Hello. So, were you the person that posted this question on the Google Drive folder?
Can you hear me?
Yeah, yeah, I can hear you now.
Oh, sorry. No, that wasn't me.
Oh, okay, okay. We'll first answer this question, and then I'll get to your questions if you have any questions. So, oh, for this one here, they were asking like, um, what was the difference between this molecule and this molecule for this HNMR practice? So we see that there's an amine on this benzene ring on the left structure, but on the right structure, this is not an amine. This is an amide where it's not connected to the benzene ring, but it's connected to the carbonyl, where we know that the more deshielded a hydrogen is, the more closer to an electronegative atom or electron withdrawing group it's going to be at. So let's see the lone pair on nitrogen right here. We see that this lone pair on the nitrogen has more resonance than the lone pair on the right structure because this lone pair can only do resonance with the carbonyl there, right? So since this amine here is going to be withdrawn more by the benzene ring, meaning that it has more resonance structures, it's going to be more deshielded, right, than usual. So amines are usually between like the 0 to 5 ppm range on the HNMR with a broad peak. But if we see this HNMR here, the amine is on 5 to 6, which is higher than usual. So since it's higher than usual, the amine on the benzene ring here is the correct structure. Right? Yeah, where we see that between 1 to 5, the alcohol or amine peak is usually around there, but in our case, we see that the amine peak here is between 5 to 6 because it's attached to the benzene ring that could do a lot of resonance. Yeah.
Got it.
Mhm. Oh, someone else wanted to join. Let's see. Hello. Were you the person that asked this question?
Yeah, I was.
Oh, shoot, shoot, shoot. Sorry, I just explained it. Is it okay if I explain this question again earlier?
Yeah, can you?
Yeah,
Sorry.
yeah, yeah, yeah. Uh-huh.
That's fine.
Yeah, yeah, no problem. So this question here, we see that we have an amine on this benzene ring, right? But on the right structure, this amine is not directly attached to the benzene ring. It's attached to the carbonyl. And do you remember the definition of deshielded, like what it means for a hydrogen to be deshielded?
Yeah, isn't it where it's like near like more electron rich regions essentially? Like say if it's an out like an sp3 is going to be more shielded than something that's not deshielded versus like alkenes, like
Mhm.
uh oxygens, etc. Electronegative stuff is going to be more deshielded.
Yeah, that's right. Electronegative stuff is gonna be more deshielded, but the better way to think about it is electron withdrawing. The more electron withdrawing group the hydrogen is near, the more deshielded it's gonna be. Right? So let's look at the lone pair on these amines here. Which lone pair do you think can do the most amount of resonance? Which can do which can move around more, which is more delocalized?
The second one on the right side.
Yeah, so the second one on the right side, let's draw the resin structure of that when we push that lone pair down and pop that carbonyl up onto that oxygen right there. This is what we get when we do that resin structure, right? And let's see here. we see let's say, oh yeah, because this double bond can actually go here, and we can move this over there as well. But when we do that, that's gonna give us, oh no, that's not gonna be that possible, because what charge would this nitrogen have if we move this double bond here? Like if we get rid of another bond to that nitrogen right there. Like right now
A
it has
negative, or
a,
it'd be neutral, right?
oh wait, so it is neutral in the original structure, but
Mm-hmm.
when we push this lone pair down here to make a double bond, this nitrogen now has four bonds, one, two, three, four,
Yeah.
and that's why it has a positive charge. But when we
Mm-hmm.
do this structure here, like let's say we have that, this nitrogen now only has three bonds and plus two charge. Does that seem very stable?
Oh yeah, because we lose octet.
Yeah, we lose octet, and that's a plus two charge, which will not like happen. It's like really rare. So that's why it will stop there. It can't do resonance with the benzene ring right there. But if we look at the amine here, this like on the left side, that lone pair can actually do resonance all around the benzene ring like that. Right? This lone pair here can't do resonance with the benzene ring, even though it looks like it can do more resonance because of the extra carbonyl here. It can't reach the benzene ring because it would reach this very unstable positive two charge here. Does that make sense?
Oh, I see. So are you saying that the one on the left would be more deshielded, correct, on the NMR?
Yeah, the one on the left would be more deshielded because it's able to do more resonance. And amines on the NMR, right? They usually show up between 0 to 5, and they show up as a broad peak usually. But on the HNMR that they gave us here, this right here is the amine peak, where that is between like 5 to 6. It's like around like 5.5 ppm, which is higher than usual, higher than what it usually is. Like usually I see around like 3 to 5, but in this case it's 5.5. And the reason why it's higher than usual is because it's more deshielded. It can do more resonance with the benzene ring.
So the one on the left would be the like correct answer, not the one on the right?
Yes, the one on the left would be the correct answer. The one right here,
Oh, okay.
where the amine
Okay.
is para to the ester.
Okay, thank you so much.
Yeah, no problem. Okay. So any other questions you guys have? If not, we could try going over like the ortho meta para definitions and what to look out for in that HNMR for ortho meta para.
Yeah, actually, I know. I think I went over the definitions, but I was looking at practice 5. I think you just scrolled down to it.
Mhm.
And I learned that it was meta, but I was really
Oh,
confused why, because it looks like an ortho, because I knew that you're supposed to look for like singlets.
right, right,
So,
right. This one right here is really like hard to read because this lab questions were like repeated from previous quarters as well. So you're right, like the meta position between two groups, there should be a singlet around here, but it's really, really hard to see the singlet peak here. Um let's say 100. Yeah, this is not like really well like given, because on the exam you'll get more clear peaks. This was used for different professors like Levens, Nisiri, Mascal also had to has to use this because this is a lab thing which is whole separate from lecture. But yeah, I wouldn't have not got meta from this too because it's too hard to read.
okay, thank you.
Yeah, yeah. Let's see. So let's do you guys want to go over the ortho meta para position definitions and what it looks like on HNMR? Okay, so um ortho, meta, and para are relationship terms where they are relationship terms between two groups. So let's say we have a benzene ring like that, and we have an R group and another R prime group. If they are one carbon away from each other, this is going to be considered ortho to each other. So we see that there are 4 benzene hydrogens here, where the benzene hydrogens will show up between 6 to 8, but it could go up to 9. So let's do 6 to 8 here. If these R groups are different from each other, then these hydrogens are all unique. There are no identical hydrogens. So if we look at this red hydrogen right here, that one red hydrogen only has one neighbor, which is the blue hydrogen. And we have to do the n+1 rule. One neighbor means n+1, 1 plus 1 is 2. 2 subpeaks or doublet. Hydrogen blue has 2 neighbors, so that's going to be a triplet. Same as the purple hydrogen, triplet. The pink hydrogen is going to be a singlet because of the number of neighbors. Okay, so if you see this pattern where all of these peaks represent one hydrogen, then you know that you have an ortho relationship benzene ring. And this is more important like for midterm 2, because you learn more about benzenes or in the ortho meta para position in midterm 2. For meta, right? We have a benzene ring and we have 2 R groups. Let's say one R group there and another R prime group here. These R groups are, let's say, 2 carbons away from each other, or like this is separation between those two. There are also 4 benzene hydrogens, and all of these 4 benzene hydrogens are also unique. There are no like identical hydrogens here, right? So the pattern that you will see for meta benzenes would be that this red hydrogen here has no neighbors, 0 neighbors. So that is going to be a singlet because 0 plus 1 is 1. This is the distinguishable feature about the meta position between 6 to 8. If you see a singlet peak between 6 to 8, then that's most likely a meta benzene ring. The blue is a doublet, purple is a triplet, pink is a doublet. So this is the pattern you see between 6 to 8 if you have a meta benzene ring. The easiest the easiest relationship to see is para. And you can think of parallel to each other, like the R groups are parallel to each other. And this time we have symmetrical hydrogens now, where these 2 hydrogens are the exact same as each other because they have the same chemical environment. This one hydrogen here is equally distant to this R group as a hydrogen right there. Like they have the same chemical environment. Like all of the other things around it have the same distance between them. Where these 2 hydrogens are also identical to each other because they have the same chemical environment. So the pattern you see for para is that you see 2 doublet peaks because each of these have 1 neighbors, but this time we have 2 H's for each of these peaks. Right. So you see 2 doublets between 6 to 8, that is going to be a para benzene ring. Okay, so this is the definition of ortho meta para, which are relationship terms, and what you expect to see on the HNMR for benzene rings. When is your guys' first midterm?
April 25th.
Oh, April 25th. Let's see.
It's week
Oh, okay.
4, I think.
Oh, okay. That's still plenty of time. It's good. Let's see. And did he say what it's on? Like what chapter is? Chapter 11, 12, or just chapter 11?
He says he doesn't follow a
Oh,
schedule.
dang. Yeah. Yeah. Like I should have came more prepared for these office hours. Like next time I'll come prepared with practice problems and stuff like that for us to try to like um yeah.
We honestly didn't get to much like last week. Like I think we did some nomenclature and
Uh-huh.
then he reviewed NMR, but he said he wasn't gonna really review it because we should already know it. And then I think class ended. So
Oh, what the heck? No, because there's new NMR stuff. Like every chapter you learn, is a new functional group, and that new functional group is like new on what you show, what you see. So he should. Well, most professors don't go over NMR anyway. Oh, wait, someone wanted to join. Wait, actually, let me just turn off the waiting room. There we go. Okay. Yeah. Yeah. So yeah, most people like most professors don't go over NMR really, unfortunately. Let's see what
Oh,
are
wait,
they.
what did Miss Gill say about the exam? Like he's not following the textbook?
Oh,
no, he is, but he just doesn't have a schedule. Like he wasn't gonna schedule what we're learning what week because he always falls behind or goes ahead.
Oh,
So he just said
got
he's
it.
not gonna like give like he made a list of the chapters we learn in 118B in the syllabus, but it's not like in order or anything.
Got it. Okay.
oh, and let me show you guys this website where it might help you guys on NMR problems for the future labs as well. Let me see, share screen. Let's say. Okay, so this is nmrdb.org, where you could draw in your structure of what you want to see and see what it looks like on HNMR. So let's try drawing like the structure with where's the benzene ring? Over here. And let's start putting nitrogen here. And parallel to that, let's put an ester. Oxygen there. Oxygen right here. Could simulate spectrum. Oh, let's go back. Mhm. Where is what's going on? Oh, okay, yeah. So I don't know where is this thing showing. Yeah, but in this case, it didn't really help because I don't know where this nitrogen H's are in the thing, but uh that's the reasoning. Like at the very beginning when I explained, it's because there's more resonance going on in that lone pair with the benzene ring, so that's why it should be the structure here. Hmm, let's see. Mm, yeah. So if there are not any other questions, we could like end this early, and when the midterm like starts approaching and you guys like start learning more lecture material, you guys can uh come in here. And do you guys have Instagram? You guys could like text me any questions you guys have as well. Like if you guys are working on practice test problems, and I'll reply as soon as I can.
What's your drop-in schedule for tutoring?
Yeah, I'll type it in the chat. So Monday, I have uh 2 to 3 p.m. Tuesday, 2 to 4 p.m. Thursday, 2 to 4 p.m. And starting on whatever week the May 6th is, because one tutor is like leaving early. I have longer hours on Monday, which is gonna be 2 to 5 p.m. And then everything else is the same. Tuesday, 2 to 4 p.m. And then Thursday, 2 to 4 p.m. I think that's like week 6. Yeah, 6, 7. Yeah, 6. Week 6 is when I have longer hours on Monday. Oh yeah, going back to the ortho meta para stuff. And also for the meta pattern, all of these peaks represent one hydrogen because there are no other identical hydrogens. But for the para one here, there's 2 hydrogens. And also another important thing is that a benzene ring does not have to have ortho meta para. Let's say we have a benzene ring that only has one substituent, one R group. Then we get 5 benzene hydrogens, where these 2 benzene hydrogens here are identical. These 2 hydrogens here are identical. And this one hydrogen right here is alone. There's no other hydrogens identical to that pink hydrogen. So let's see what this would look like between 6 to 8 on the HNMR. So the red hydrogens, like we focus on only one. They have one neighbor, so that should look like a doublet. The blue hydrogen, there's 2 neighbors, so that should be a triplet for the blue hydrogen. And for the pink hydrogen, there is only one neighbor. Oh wait, actually 2 neighbors. 2 neighbors for the pink hydrogen. One here and another here, so that should also be a triplet. Where the red hydrogen peak has 2 hydrogens, the blue hydrogen peak has 2 hydrogens, and the pink hydrogen peak has only 1 hydrogen there. Right. So this is the pattern you see if there are no other R groups attached to the benzene ring. Yeah. Which I think could show up on the midterm 2 though. This would not show up on midterm 1. Like these things here would not show up on midterm 1 because it's most likely going to be alkenes and alkynes only for midterm 1. Yeah. Any other questions?
No, thank you.
Yeah, no problem. Yeah.
Um, for your drop-in, your hours, are they like going to be on Zoom?
So
The
the
ones that
drop-in.
you post.
Oh, these
Sorry, not the
drop-in.
drop-ins.
Uh-huh.
The hours you posted in the chat.
Oh, on the Zoom chat.
Mm-hmm.
These hours I dropped are my drop-in hours at ATC at the library. You know the
Okay.
lower level of the library where like the ATC tables are.
Yeah.
Yeah, these are my shifts, like when I work. But there are other tutors there as well, like on the other times that I'm not there.
Okay.
But I'll
Okay.
host these Monday, Tuesday, Wednesday, Thursday, 9 to 10 p.m. But for this one, there's like not a lot of questions because like we barely went to any material. But I hope today's office hours helped like with these ortho meta para stuff. Yeah.
Yeah, it helped a lot. Thank you.
Yeah, I'm glad. No problem.
Okay. Have a good day.
Yeah, you too. See ya. Bye.